Hello everyone. We're going to get started with our webinar on making modeling and simulation widely available on the web. My name is Lisa Avila. I'm one of the founders and the CEO of Kitware. I'll be speaking with you for just a few minutes today to welcome you and give you an introduction to Kitware. Then I will pass things over to our speaker today, Cory Quammen. He'll talk about the motivation for and the advantages of having modeling and simulation applications available on the web. He'll cover the components you'll need to do that, and then he'll go into a deeper dive into how our open source tools can help you with that. He'll show you some demos of that, and then he'll wrap up with some information on next steps you can take. And don't worry, there's going to be a lot of links and information on these slides, but you don't need to try to copy those down. After the webinar, we will be sending you a copy of these slides. And we will be pausing throughout the webinar to answer your questions. If you look in the upper right corner of your screen, depending on how you have it configured, you'll probably see a little speech bubble with a question mark inside of it. That's the area for questions. Click on that and type your questions in there, and we'll get to it throughout the webinar. We'll also have some time for questions at the end. So Kitware is a software and AI research and development company. We have about 200 employees. They're across our offices that are here in the US and over in Europe. We've been around since 1998, and we are committed to open source and open science. We're proud to be a 100% employee-owned company. We're also a highly collaborative company. We work with many academic, government, and commercial partners on some very large research efforts, and when possible, we like to share the results of those efforts through our open source platforms. We also provide training, support, and commercial research and development services related to those platforms and our various expertise areas. Our primary focus areas are in healthcare and life sciences, energy and manufacturing, and defense and intelligence. We're most known for our open source platforms and the vibrant communities that we build around these platforms. These are some of our top open source projects, many of which have been going on for more than two decades. And so with that, I'm going to turn things over to Cory.
Thank you, Lisa. Hi, everybody. I'm Cory Quammen, technical leader here at Kitware, just about to celebrate my 11th year with Kitware. I'm really excited to be here to tell you about some of the approaches to make your modeling and simulation software widely available on the web. So this webinar is intended for a few different types of people. If you're a contributor to an open source modeling or simulation software and want to provide web-based access to these tools, this webinar is right for you. If you're a software engineer looking to solve a specific problem in your web-based simulation application and you want the benefits of a commercially friendly open source software, this webinar is right for you. And if you're a product manager of a modeling and simulation firm and you want new options for delivering your software, this webinar is right for you. If you're just curious about running simulations through a web interface, this webinar is also right for you. And no matter who you are, I'm just happy that you're here and watching this webinar. So thanks for attending. First, I want to start by telling you what I mean by modeling and simulation. I'm using these words, which are overloaded quite frequently, in the context of running computer software that models some kind of physical phenomenon in the real world. By modeling, I mean the creation of data structures, such as meshes that are needed to discretize the mathematical model that describes the physical phenomenon, then the definition of parameters that might also govern that phenomenon. By simulation, I mean the process of computing the modeled phenomenon in a way that produces data that reveals how that physical phenomenon has evolved. So in practice, modeling and simulation is carried out as part of a workflow. This is just one example of a modeling and simulation workflow. On the left, we have model creation and domain definition. This can involve creation of geometry that represents some physical objects in the world, as well as an embedding in which those objects interact with some external components. So for example, we might have a model of an airplane wing that interacts with a volume of air that's flowing around it. To the right of that, we have discretization or meshing. In many simulations, this step is critical for getting accurate results. Third in line, we have parameter specification, which is where you specify input parameters that affect the evolution of the physical phenomenon. This might involve, for example, setting boundary conditions or defining things like Reynolds number in the computational fluid dynamics simulation. Once everything is set up in terms of having a mesh, if it's required, the model parameters, the simulation process, and the model parameters are set, the simulation process can begin. This is the actual computation of the model and the simulation results that we are running. Finally, to understand the result of the simulation, we have a post-processing step that involves analysis and visualization of the data that's been generated by the simulation. Now, from there, we can adjust the discretization or parameters used as input and run the simulation again and see how the results differ. So for example, we might be optimizing the position or angle of a spoiler on a car in a racing application. One parameter we might be trying to optimize is the angle of that spoiler, and so you can run simulation with one angle value as a parameter, check the results, and rerun the simulation and optimize that angle in the end. So looking at this workflow, the important part is that you want to move your modeling and simulation elements to the web. If you want to do that, you have to decide how you want to move each of those components there. So the components I've outlined in red here are the areas of the simulation workflow that we'll concentrate on today. So an assumption is that the meshing and simulation software itself is best left as software executables that will be run on some cloud instance in the web application backend rather than in the browser, right? That usually requires some hefty computational power to do that. But we're not going to focus on that part today. Instead, we're going to focus on these three highlighted parts. We'll focus on the interface tools to help you with model creation, domain definition, parameter specification, and post-processing, including visualization and analysis. So when I say, or what the title of this talk is about making modeling and simulation widely available on the web, I want to clarify what I mean by that. So I'm not talking about a web application that is something like a remote desktop application or a thin client that simply provides a window into some remote system where the usual desktop software is installed. Now that's a fine model and has plenty of benefits. In fact, a number of software simulation software providers offer such services, and they work well. But this is not the model I'm talking about today. Instead, I want to talk about native web applications that are delivered from a web server to your web browser. Now, web browsers these days are very capable platforms for software application delivery. They offer advanced user interfaces that are as good as, and in some cases even better than, desktop applications. You might be familiar with Microsoft's suite of Office applications that are available online. Adobe offers their tools such as Photoshop, Premiere, and Illustrator online as well. And this is a great platform to offer those tools that have historically been desktop applications. You're probably familiar with other services that you use every month to do banking or pay bills. Those are all web applications with usually fairly nice interfaces. These days, there are a lot of software tools available that make it routine for web developers to build attractive user interfaces that are perfectly suited to what we're interested here today, which is modeling and simulation applications. So why put modeling and simulation applications on the web? So if you're attending this webinar, you probably already have some kind of answer to that question of why you should be putting modeling and simulation applications on the web. I'd like to put a few additional reasons out there for you to think about. One reason is that end users can avoid buying and maintaining expensive computer hardware that they keep and administer on premises. If you provide your model and simulation application on the web, that alleviates the need for your customers to purchase and maintain that hardware. And at the same time, your customers can benefit, and you can benefit from the scalability offered by cloud computing services. As demand for the simulation service increases, you can provision additional hardware that's used to run them with ease. In addition to potential cost savings and scalability, Putting modeling and simulation software on the web makes it available via web browser on virtually any device. That device could be a laptop computer, desktop computer, or even your mobile phone. So just think about running simulations, setting them up, and running them, and looking at the results from your mobile phone. Pretty cool reality we live in these days. So by putting your simulation software on the web, it's basically available everywhere. There are a few additional reasons to put modeling and simulation applications on the web. Often simulation software consists of an ecosystem of very different executables that are used together to produce that simulation workflow we saw earlier. These applications can be pretty complex to use by themselves, let alone in the sequence you need to produce simulation results successfully. So integrating them behind a single user-facing application that hides away those details of using them just makes the software easier to use and increases the adaptability of your software by users. Because people can connect to that simulation software from anywhere on the planet when it's on the web, having that available online also opens up possibilities for easy collaboration. For example, design teams from even different continents can log in to the same website and share models and simulation results among each other quickly and easily. Putting simulation software online also opens doors to non-expert users who are unlikely to have access to a workstation where traditional desktop modeling and simulation applications would usually be installed. You can even go one step further and make it possible for computational scientists to create curated simulations that have only a few exposed parameters that are meaningful to end users who have other expertise, not necessarily computational modelers. I'll demonstrate such an application a little bit later on. The value of doing this is that it has a multiplicative effect on the value provided by computational scientists within an organization, since they can delegate some of the more mundane but still necessary simulation tasks to others who weren't able to run simulation software easily before. Finally, putting modeling and simulation application on the web opens up potential for new revenue models. So for example, in addition to licensing per user for some period of time, you can charge fees by different metrics, such as per simulation run. Now, I'm not the first one to identify benefits of putting simulation software on the web. There are a number of simulation software providers that have made this realization and recognize the value of offering web-based applications. A few of them are listed here, and these are, again, talking about web-based applications, not necessarily offering remote desktop solutions. So clearly there's industry buy-in to this idea, and we expect to see more and more simulation modeling offerings on the web going into the future. So we saw earlier a depiction of one possible workflow for modeling and simulation. What are the components that we need to enable the creation of those workflows on the web? So first, we need some kind of geometric modeling tools. This might consist of like a database of predefined model geometries, or maybe simply text descriptions of a model geometry and how their different objects are related to each other in space, or even full-fledged CAD tools that let you in 3D interactively define input model geometry. Second, we need some kind of user interface elements. These could include text fields to enter numbers, sliders to specify numbers within a range, checkboxes to turn options on and off, list trees, and so on. Things you would typically find in a simulation program. Web applications use these elements to set simulation input values, for example, in a web-based simulation app. Third, we need some kind of compute resources for running the simulations. These could be on premises if your web application is running on premises, or they could be cloud compute resources. And they might include a GPU for GPU optimized codes, or even for image rendering, which we'll touch on a little bit later. Fourth, to make the results of the simulation interpretable by people, some analysis and visualization tools need to be included. These could include simply tables of numbers or 2D plots or 3D visualization, as well as report generation, generating PDFs or some kind of whole report to send to decision makers. So lastly, a data management system of some kind is needed to keep those inputs to the simulation and the outputs from the simulation organized. This management system should provide things like access control and other things that are typical for maybe data archiving and so on. Now, there are a lot of software packages that are available to help with the tasks I just described. As a company that specializes in open source software development and support, Kitware recognizes and promotes the value of using open source software to aid in the development of your web-based modeling and simulation applications. Many others do as well. Let me share with you a couple of reasons to use open source software. First, open source software lets you jumpstart your application development. So by satisfying a common software need with an existing open source library, you can focus on the value your software provides instead of reinventing the wheel. In addition, there are no costly licensing fees. A lot of open source software is licensed in a way that lets you use it in commercial offerings without owing any kind of licensing fee. Open source software also helps you avoid vendor lock-in. While there's a labor investment required to use any open source software library, there are no other really financial considerations to make that have the effect of keeping you locked into using that software. You can freely swap it out for another open source library that does the same task. Open source software also has the benefit that bug fixes and updates are contributed by others that use the software, and you benefit simply by updating software for free when a new version comes out. You also have the option of contributing features and bug fixes that are of use to you back to the open source software project so that others can benefit. It's a real win-win situation. Another benefit is that the code is opened and can be scrutinized for security flaws or other problems by anyone. So this can provide assurance that the software you're using is secure and that any flaws that are found can be remedied. Finally, a lot of open source software projects have professional support available should you need it. That's true of the software tools I'll be talking about in the rest of this webinar. So returning to the topic of what you need to produce a web application for modeling and simulation, you have a choice to make in terms of what web user experience ecosystem you're going to use for the front end or the user-facing portion of that application. So a web user experience ecosystem takes care of a lot of the application details, and it typically handles things like browser compatibility issues and adapting to mobile display layouts or laptop display layouts, for instance. Many of these allow you to provide a customized look and feel for branding purposes with consistency across user interface elements. Popular ecosystems you might have heard of are React, Vue, and Angular, but there are others. Each of these ecosystems have different user interface libraries that you can plug in and use in your application to provide all those user interface elements. And all of these happen to be open source too, by the way. Once you have a user experience and user interface library selected, you likely want to provide some kind of visualization and post-processing tools in your application. For understanding simulation results, 2D plots like bar charts, stack charts, scatter plots, and so on are a key element in data analysis and report generation. Fortunately, there are a lot of very good plotting tools available for use on the web. These integrate with your web application in a pretty straightforward way. Examples of these libraries include Dash, Vega Altair, and DeckGL. For simulations of 3D phenomenon, interactive 3D visualization is often a key component in applications that let you understand those 3D simulation results. Now, a question arises, how do you achieve 3D visualization in a web browser? Now, let's just assume that we have some server process that's running and at least serving our web application to the web browser. but it's also doing other things like loading or simulation data, maybe applying some filtering operations to do things like extract cut plane generation or create isosurfaces. So with this basic client server setup, there are a couple approaches that we can use to generate images of 3D data for display in the web browser. The first involves doing all the rendering on the server. So in this approach, the data that resides on the server and is already loaded in the server process is rendered by that same process. The image that results is then transmitted back to the browser for display to the user. Interaction involves taking mouse clicks and movements from that browser that the user has input and converting them into requests sent back to the server to tell it how to change the 3D view. So after that happens, the server generates the next image and sends it over to the client. Client does some interaction, makes a request back to the server, and so on. And this process continues. And if it's fast enough, it results in interactive visualization. But again, that's where all the image generation is done on the server. There's a second approach to generating images of 3D data, which is to extract and transmit some geometry from the server to the browser. Now, once it's in the browser itself is responsible for generating the 3D image using some 3D graphics library that's written at some level in JavaScript. Now, the same mouse clicks and drags in the render window can have some interactive effect on the 3D view in the same way as in the first approach, but all the interaction can be computed right in the browser, and there's no communication that needs to take place between the server and the browser. The end result is again 3D interactive visualization, but without the addition of lag time that can result from client-server communication. Both of these approaches have pros and cons, and the first approach is good if the geometry is, say, too large to efficiently send to the browser, and you have a GPU that's available to do the rendering on the server side. Rendered 2D images, especially with some compression, are much smaller to send to the browser than large geometry. And even if they're sent frequently, it can be more efficient than not sending that full geometry. Meanwhile, the second approach typically gives better 3D interaction because, again, that lag is missing between the client and the server. Everything's happening on the browser side, so you get a bit more interactive, more responsive interaction. The catch is that 3D libraries for rendering on the browser has to be capable of generating the kinds of images that you typically want to generate in post-processing. Now, in practice, both of these approaches are used. The same application can even switch between these approaches depending on things like the size of the data or the network latency between the server and the client to give, in the end, the best user experience. I'm going to dive a little bit deeper into the 3D visualization aspect of the post-processing. So at Kitware, our preferred 3D rendering and scientific visualization technology is the Visualization Toolkit, or VTK. For nearly 30 years now, the software library has enabled creation of interactive 3D visualization of the many kinds of data one finds in the scientific and medical domains. That also includes molecular data, medical images, engineering data, Earth system data, astrophysics and cosmology, and computational fluid dynamics, just to name a few. These screenshots here are representative of VTK's capabilities. All major scientific visualization techniques, such as cut planes, isosurfaces, volume rendering, stream tracing, glyphs, and color mapping on surfaces and in volumes, are supported. VTK is a software toolkit for visualization. It's written in C++ and runs on Linux, Mac OS, and Windows. It also has language wrappings for Python, Java, and C#. VTK is open source and has a permissive BSD style license, which means it can be incorporated into commercial software products. VTK is able to work with several different user interface toolkits, including Qt, MFC, X11, macOS Cocoa, and several Java toolkits. But wait, I just said VTK is a C++ library, and really it's intended for traditional desktop software. So how do you use it for visualization on the web? Well, there are two different approaches available at this time to use VTK in web applications. One is with the JavaScript library called VTK.js. The other is with VTK C++ code compiled to WebAssembly. We call the second approach VTK WASM, where WASM is an abbreviation of WebAssembly. All right, so we have these two different approaches. So what are the similarities and differences between them? Why do we have two different approaches? So both are libraries that that enable rich 3D visualization on the web. They provide similar functionality in terms of the core scientific visualization capabilities that they provide. VTK.js is a rewrite of parts of VTK that are relevant for web-based scientific visualization viewers. It's not a complete rewrite. It's only a subset of VTK that was written in pure JavaScript. It uses WebGL2 and optionally WebGPU to generate 3D graphics. Those are both 3D rendering libraries available in web browsers. VTK.js provides features such as polygonal mesh display, pseudo-coloring, volume rendering, and interactive widgets, all of which can be used to make these compelling visualization experiences in your web browser. By the way, VTK.js was the topic of a recent webinar Kitware gave, and that link is here in the slides if you wish to view a recording of that webinar after this presentation. So I'm going to show you now a couple demos of VTK.js renderings to just give you an idea of its capabilities.
This probably is a good time, Cory, to break in with a question that came in. Your demo might cover it, but I remind everybody that demos through a webinar interface sometimes seem choppy when they're perfectly smooth to Cory. But the question is, what kind of rendering performance could you expect to get out of a web browser?
Right. So most recently, we've been developing in the VTK WASM interface, which I'm talking about next, some optimizations that let you render tens of millions of polygons, 10 to 20 million polygons at interactive frame rates, so 15 to 30 frames per second. One of the limitations that we run into using that approach is, or has been until recently, a 32-bit memory address space. So you can often run out of memory before you run out of rendering performance or how many triangles you can render. That's been alleviated, and 64-bit address spaces are now available. So we can really push that. But yeah, on the order of 20 million polygons at interactive rates is quite possible. Thanks for that question. Yes, so here is an example of a visualization. This is just a pre-canned. It's not interactive other than I can slowly move because this is very interactive on my system, but as Lisa had mentioned, it's subject to compression and is a little bit less smooth on your side. But it basically shows a couple of things. We're showing geometry here in a mixing vessel application. This vessel is set to transparent, and so you can see that transparent compositing is done in a correct order. We have pseudo coloring on these streamlines that are displayed here. So, classic example of scientific visualization here, and this is VTK.js. Next, I'm going to show volume rendering. So this is a medical data set. So volume rendering is a way that lets you see through 3D data. It's a transfer function, which is shown in the upper left here, modifies how data values are mapped to both color and opacity. And so as I'm adjusting that, you can see the results. It might be a little subtle, but you can say focus more on bone than flesh as I move this transfer function around. But this is all happening and rendering very quickly. This is a VTK.js volume renderer. And I'm still, to this day, amazed to see this work so smoothly on web browsers, especially on my phone when I look at that. I never imagined the day when we'd have volume rendering on phones work just very smoothly. So that is a quick demo of a couple of the capabilities of VTK.js. So next, I'm going to tell you about VTK WASM. So VTK WASM consists of VTK components from the C++ VTK original library that are compiled into WebAssembly. Sorry, I've been saying WASM. WASM is just a shorter way to say WebAssembly. So these C++ VTK, this C++ VTK code is compiled into WebAssembly, which is a binary instruction format that can run in a virtual machine in your web browser. Mscripten is the compiler tool chain that allows you to do this, and it actually is pretty neat because it will take those OpenGL calls in VTK and transpile those into WebGL2 calls. So a cool thing about this is that that same C++ code that you can use to generate 3D images in a traditional desktop application, or say if you're doing server-side rendering that I described before, can be brought into the web browser and can be used to do 3D rendering right in that web browser. WebGL2 has some capability limitations that making developing with it challenging at times. But as we look to the future, we are currently in the process of implementing a rendering backend that uses the more modern WebGPU 3D library or interface that is actually pretty bleeding edge, but it offers an opportunity for us to target both rendering in the web and desktop with the same backend using either our regular C++ compilers or Mscripten. So I'm going to show you now a couple of demonstrations of C++ VTK compiled with Mscripten into VTK WASM examples running in the web browser. So this isn't really scientific data, but I thought it was a cool example because it just shows you that C++ VTK code is running in the web browser and lets you have nice things like textures, nice lighting effects. You see how the metal shows up, some physically based rendering capabilities. So it's low on the scientific merit, but it is a good example of what rendering is possible in the browser. And remember, this is a C++ VTK example running. It's not in VTK.js or some other library. Here is a more relevant example. This is, again, a VTK C++ application. This is from the VTK C++ examples page. That shows some simulation of a fire and airflow related to that. So you notice I'm pulling this user interface element that's actually rendering just right into the 3D scene. It's a slider. I'm moving the kind of pinkish sphere up and down, and you'll see that the streamlines are changing. Right? So this pink sphere is the seed point location, and all the streamlines are coming out of it. The thing to realize is that this is all being computed right in the web browser. The streamline integration included. It's all contained in this one application running here. There's no server on the back end. So it just gives you an idea of some of the power of what you can do with native, or well, VTK C++ compiled into WebAssembly and exposes an application this way.
All right, I think this is a good time to jump in with another question that came up.
Sure.
Somebody wants to know if you can just write your web application in C++ and compile it to run on the web.
Yeah, so that's partly true. So if you just change your compiler to Mscripten, that takes you all part of the way. But there's still some JavaScript wrapping you need to do to basically start that WebAssembly code running, and then provide things like the user interaction that you saw when I click the mouse and drag it around to do the 3D. So it's not necessarily that you can just take a stock VTK program and put it on the web. There's a little bit of JavaScript to write, but the 3D rendering components are fairly straightforward to compile.
Thanks, Cory.
Yeah, great question. Thanks. So we covered those two different approaches. I expect to see more and more progress from VTK WASM, and meanwhile VTK.js is going to continue to be strong as well and let you make compelling visualization applications on the web using either one of those. So next I want to turn my attention a little bit to a nice tool that's come out in the last couple of years out of Kitware here. And we call that tool trame. So trame is a Python framework that lets you efficiently build web visualization applications. It ties all the rendering components that we talked about, client-server communication components, and user interface definitions, and some control over the UI style, all into one easy-to-use package. It makes available in an easy way all the best practices that over the last 15 years of web visualization development at Kitware have been identified. So trame lets you skip writing a lot of the web boilerplate involved in making a web visualization application. You don't necessarily need to, don't explicitly need to grab one of these user experience frameworks like Vue or React and start building your application from that. Trame comes with support for Vue.js and Vuetify to provide the UI components, and gives you a pretty easy way to define those components and hook them up to code that runs in your Python-based application. So it lets visualization programmers without much web development experience build web applications. And it enables experienced web programmers to build web apps faster for prototyping purposes. So I want to tell you about next week. There's a webinar at the same time that goes into much more depth about trame. So if you look on our website, or there'll be links in this presentation deck that we send you, so you can register for it and check it out. So let me demo real fast one example application built on trame. This is called VeraCore, and it's for visualizing nuclear reactor core components. So you can see some of the user interface elements here. We have different views of the data. Here's a 3D volume rendering view. And this is all rendered on, I believe, the server side, and the frames are sent for display on the browser here. It does connect to a backend server, and that's doing the rendering here, as well as providing all the other data to the browser here. You can switch different view types of the data. You can rearrange these components, and this is all courtesy of Vue, taking care of that for us. You can switch which things you're looking at, the menu interface here. So all the, this is a very nice application for understanding this kind of data. There's also different time steps available for visualization. You can switch to those with the slider bar at the bottom. So really, this gives you an idea of all the user interface elements you can find, all in Python, all with trame, and then have that, most of those details, any kind of JavaScript or anything is hidden from the developer. They just don't need to know that with any great detail. So another visualization platform that you can use for 3D rendering on the web that you might consider for modeling and simulation applications is ParaView. So ParaView is definitely a desktop application. It also runs on servers. It's built on VTK and adds parallel data processing capabilities. It's targeted for use on HPC systems. So it can be run in a client-server configuration with the 3D interactive display on the client side, like we've been talking about in the browser, and the server that's running on a system that has access to the file system where all the simulation output resides. And that's often the same system that ran the simulation. So because it's a VTK-based application, that means that trame can be paired with it to do web-based 3D visualization. So you can actually have a ParaView server running on an HPC system, serving data to the ParaView client, and then the trame application interacting with that client to generate 3D data or grab geometry and display that in your web browser. So if you've got large data or you're involving using HPC systems, this is a possibility. Okay. Next, I'd like to put this all together in the in a kind of a capstone project of sorts, and show you an example of a web application that provides end-to-end modeling, simulation, analysis, and visualization. This application is called ArrowFlow, and it's a web application offered by Kitware that provides end-to-end simplified workflows for the MStar CFD simulation code. I'm going to get that loaded up here. So when you go to an ArrowFlow installation, there is a server running, and when you connect to it, you're initially presented with a set of simulation scenarios here. Here we have 3. There's an agitated tank model and a couple others here as well. So the idea would be that some computational scientist has defined these models and made them available to other people who maybe don't know the physics as well, but do know certain things, like rotation speed. They can set that, or how high a liquid level needs to be in some kind of mixing application, when to inject dye that's used to trace the mixing or the time it takes to mix things. They can adjust those parameters and not worry about some of the more intense physics that the computational scientists would have to worry about. So this lets you pick a model. It lets you set a couple simulation parameters, like you see here, and we're going to load an existing run. I could run it live here, but it takes a little bit of time to start up the simulation. So let's load up an existing run. So this was pre-computed, but if you were starting a new run, you would see this view, and you would see new time steps come in as they're calculated. Up at the top, we have a slider that we can play through the simulation over time. You can see the liquid surface is starting to move as this impeller is rotating around. Now, if I stop it here, we also have a plot on the right that shows different quantities. In this case, it's a quantity called moving body power. But we can look at a number of other items in here too, like the kinetic energy of the fluid. If I adjust some of the simulation or the visualization parameters, I can see velocity magnitude of fluids in this 3D view. Now, all these images are being rendered on a server that is located, I believe, in New Mexico. I'm in North Carolina, so it's across the continent, and I'm getting pretty interactive response here, which, sorry, that doesn't necessarily convey it completely in the webinar interface. But we can watch this process evolve, do some analysis, make some conclusions, and then we can start over and run a different set of parameters. Here's a table of all the results, or all the runs we've made before, listed by different parameter combinations. You can load them up with these icons on the right here, or delete them. So, it's a nice compact application that gives you end-to-end modeling from problem setup to post-processing. And that really encapsulates the idea I'm trying to convey in this webinar. Okay, so wrapping up here. Now we have lots and lots of example applications that use trame, VTK, or ParaView to do rendering on the web. This slide has links to all these examples in their source code repositories, and even in some cases the live demo in the case of this VR Core application. So check that out when you get a copy of the slides. Now, where does Kitware fit into all of this? So we contribute quite heavily to the open source software tools that are useful for modeling and simulation on the web, especially on the post-processing side and even on the pre-processing side. So it includes the tools I talked about in detail today, the visualization toolkit, trame, ParaView, and then I haven't mentioned too much, but we have a whole data analytics team here who specializes in data management, and they have a framework called Resonance that they can use to make data archiving and data handling kind of basically a file system to store simulation results and input. So we have a lot of tools available and a lot of expertise in how to use them and put together the different tools into modeling and simulation applications on the web. I wanted to, again, mention that trame webinar next week. So go here and click on this graphic in the slides. You can register and sign up for that. Past webinars have included more detail on VTK.js and this open source visualization and data analysis in the browser webinar. And then a related but somewhat different, less web-oriented, but still simulation workflow and making that easier for end users, given by Bob Barra about the computational model builder in this last link here for quickly creating, deploying, and maintaining simulation workflows. So lastly, I'd just like to let you know that Kitware can be your partner if you decide to pursue putting a modeling and simulation application on the web. First of all, you can go check out these tools, VTK, VTK.js, and trame. Those are all freely available in open source to use with licenses that let you use them in commercial offerings. If you need help, there are public forums where you can ask questions for VTK, VTK.js, and that includes VTK WASM, or ParaView, or trame. If you need more help than that, Kitware offers professional services, including rapid response technical support, where we help you get past thorny technical issues or questions you might have. We can do custom web app development for you, either as part of your development team, or we can do the entire project for you. We also engage in a lot of collaborative research, as Lisa said from the outset. We can be involved as co-PIs or subcontractors on different federal opportunities that come up. So if you're interested in working with us or finding out more, there's a link at the bottom that lets you contact us. So with that, that's the end of my presentation today. I thank you for your attention. I'm happy to answer any questions that might be outstanding.
If you have any last minute questions, enter them in that question area. Otherwise, we'd like to thank you for attending this webinar. Again, we'll be sending out the slides afterwards, and feel free to contact us at any point if you have any further questions or need any assistance. Thank you and have a great day.